I want to look at thin film interference, but what exactly is a thin film? So here are some examples. Maybe I have a layer of oil on water. So I have air, and then I have a layer of oil, and then I have some water. The oil would be considered a thin film. Maybe I have two glass plates. So I have a plate of glass, then an air gap, and then another plate of glass. So in this case, the air gap would be considered a thin film. And finally, I could have a soap bubble. So I could have air, and then I could have a layer of soap, and then I could have some more air. In this case, the soap would be the thin film. So why do we care about thin films? Well, it turns out that they can exhibit interference patterns. So here's an example. Let's look at the soap bubble again. So we have air and then soap and then air, and the soap would be considered the thin film. And you've probably seen something like this before, where you have a thin film of soap and you can see a bunch of bands on here and different colors. This is an interference pattern. Here's another picture, and you can see in this case we have thicker bands, and again, different colors and spots that are brighter and other spots that are darker. Okay, so let's look again at air, oil, and water. And let's try and understand why we're getting the interference pattern. So I'm going to consider light rays that are perpendicular to the surface of the oil. But I want to actually see what's happening at each of these boundaries when it reaches the oil, and then when it reaches the oil-water boundary, and then when the reflection happens and we have the oil-air boundary. And that's going to be kind of hard to draw if I have all of my light rays perpendicular. Everything's going to be on top of one another. So instead, I'm going to draw it so that the arrow is coming in at an angle. But just keep in mind, I'm doing this just so that you can see what's happening. In reality, I'm looking at light rays that are perpendicular to the surface. Okay, so a light ray comes in, gets to the air-oil boundary, and some of it gets reflected, and we use the law of reflection here, where the angle of incidence equals the angle of reflection. And some of it gets refracted. So there's the refracted ray. And then we have an oil-water boundary. And so again, some of this gets reflected and some of it gets refracted. I'm not going to draw the refracted ray because I don't really care about that one. I just want to look at the reflected ray here. And now I have an oil-air boundary once again, and this time some of it's going to get reflected. I won't draw that ray. And some of it gets refracted. So in this case, what happens is that I have two rays that if there were a person here, they would observe these two rays, and it's the difference between these two rays that's causing the interference pattern. So we see if we have a ray 1 and a ray 2, that it's the difference in ray 1 and ray 2 that are causing what looks to be like the bright spots and the dark spots. Let's call this point A, where the initial ray reaches the air-oil boundary, and let's call this point B, and then we'll call this point C. And so I can say that if R1 and R2 are in phase, then we have constructive interference, and the region AC appears to be a bright spot. Remember that I actually have rays that are coming in perpendicular to this rather than at an angle. So in that case, the region around where the light ray reaches the surface would appear to be a bright spot. If R1 and R2 are out of phase, then we have destructive interference, and the region AC appears dark. Okay, so how could we try and figure out when we're going to have constructive interference and when we're going to have destructive interference? Well, there's three factors that can affect the phase difference: reflections at boundaries, path length difference, and different media. So let's look at each of these individually. So first we have reflections at boundaries. So consider a pulse traveling along a string. If I have a pulse traveling along a string where the string is maybe tied around a pole at one end, so that means that the string is free to move up and down right here. Well, in that case, when the pulse reaches that pole, it's going to travel back in the same direction, and it won't be inverted. In other words, there's no phase change here. It just turns around. But if I have a pulse traveling on a string that's tied to a wall, so that the string is stuck right here. It can't move up or down. In that case, after it reaches the wall and turns around, it becomes inverted, and that is a phase change. And it turns out that something very similar is happening to light when it reaches a boundary. So let's look at, say, a light ray coming in at an angle and then leaving at another angle, and we'll say that this is medium that has an index of refraction of n1, and this is a medium with an index of refraction n2. And if n1 is greater than n2, there is no phase change upon reflection. That's like the rope that was tied around the pole. However, if n1 is less than n2, then there's a 180-degree phase change, or pi radians, or half a wavelength, phase change upon reflection. Okay, what about path length difference? So here's the air, oil, and water picture from before, and let's say that the oil has a thickness L. Well, remember that the ray of light is actually perpendicular to the surface. I didn't draw it that way here because I wanted to show all the reflections and refractions, but remember it's actually perpendicular. And so the path length difference is 2L. Why is that? Well, the incoming ray right here did not enter the oil at all for ray 1, but for ray 2, it entered the oil, traveled down a distance L, and then back up a distance L before coming out. So that would be a path length difference of 2L. What about different media? So let's say that the index of refraction of the oil is N. Well, then I know that the wavelength of the light when it's in the oil equals the wavelength of the light in vacuum divided by the index of refraction. So this lambda sub n, that's the wavelength in the medium with index of refraction n. This lambda is wavelength in vacuum, and the n is the index of refraction. And we care about the lambda inside the thin film because it's the thin film that's the difference between R1 and R2. R1 does not enter this thin film, while R2 does come from the thin film. Okay, let's put it all together. So imagine that we have air with an index of refraction 1, we have oil with an index of refraction 1.25, and then we have water which has an index of refraction of 1.33. So we see at A, there is a 180-degree phase change. We're going from, at this point right here, we're going from N1 to N2. That means a smaller value of N1 or a smaller value of index refraction to a larger value of index refraction, and in that case there is a phase change of 180 degrees. At B, that's down here between the oil and the water, again we have a phase change because we're going from 1.25 to 1.33, which is larger. So that means that our maxima are going to be at the places where we have a path length difference equal to an integral number of wavelengths. And why is that? Well, this is the normal formula that you would use for maxima. And these two phase changes essentially cancel each other out. We had 180 and then another 180, so we're kind of back to where we were. So this is just the normal equation that you would use for maxima, where m is any integer. And since I know that I have a wavelength inside the thin film, I can rewrite that in terms of a wavelength in vacuum, and it would look like this. That means that the minima are going to be at m plus a half lambda over n. Okay, let's change things around. Now let's have, again, air, index of refraction 1, but now let's make the oil have an index of refraction of 1.40, and then the water is still 1.33. So in this case, we still have a 180-degree phase change at A, but now at B, there's no phase change. Why is that? Well, look at B, that's right here, and then we're going from 1.40 to 1.33. 1.33 is smaller than 1.40. That's no phase change there. So now the maxima are going to have a formula that looked like the formula for the minima that we had before. It's going to say that the path length difference is m plus a half times lambda over n. And the minima are going to have a formula that looked like the maxima before. 2L equals m lambda over n. So when you're doing problems with thin film interference, you're always going to have these two formulas. It just might change which one refers to where the maxima are located and which one refers to where the minima are located. So in order to determine which formula goes with which situation, Look at the reflections at each of the boundaries. Then see what the total phase change is and use that to determine where the maxima are and where the minima are.